So then, let me show you the question first. Our computing problem number 8. Count binary digits. The title. Let me give you the problem. Given a positive decimal integer n, by default, so given integer, it's decimal, but here, why I emphasize decimal here, right? The reason is later, I will talk about binary. So that's the reason I mentioned this decimal first. Find the number of binary digits in its binary representation. We know binary digits, we usually call it bits, right? Bits. But here, binary digits, the meaning, original meaning, all right? Now, let us solve this problem. It looks not too hard, right? Given arbitrary positive integer n, find the number of binary digits or bits used in its binary representation. Right, so it's not hard. Remember our first introduction recursion problem, we start with factorial. That is not hard, that is very simple, but we can learn something useful from a simple example. Here, the similar situation, we have a lot of useful things we can learn. So let's do the analysis. All right. Here is the reference on our textbook. Okay. Analysis. So let's review the binary representation. In your discrete math, you learned binary representation, the standard binary representation. It's like this. Okay. N equals, then we have a sequence of bits. Here I arrange from the least significant bit to the most significant bit. V0, the least significant bit. V sub s, the most significant bit. All right, so that's the standard form. Obviously, V sub s cannot be 0. Otherwise, we reduce s by 1. Oh. Some noise, microphone. Let me see. Oh, Lubaba. So your microphone, you need to turn off. Okay. All right. So that means B sub s must be 1. Okay. If it cannot be 0, it can only be 1. All right. Then, now let us look at the answer in this representation. We can immediately get our answer expression, that is s plus 1. But the question is, here in your answer expression, you use s. And our given data, that is n. So when you have an expression not using the given number n, you need to do the conversion. You need to write this s plus 1 in terms of n. Because we do not know how large is s, right? So we need to write s in terms of n. Okay, all right. Still, we need to do some work. Otherwise, s plus 1, that's the answer. Not yet. You need to do some more work to find expression of S. Okay, yeah. Here, how to complete that step, that important step for this question. Here, I like to give you some insight how to get that step, the insight. So the insight here is because from this standard formula, this is the standard binary representation form, we do not feel we can see the answer easily. Yeah, it's still hard to see, you know, S expression in terms of M easily. Yeah. So we need to have some more friendly form. Yeah, this current form we feel not that friendly to discover expression for S. So we are looking for a different form, a more friendly form. Yeah. So here, the insight, how to find the insight. Here, I like to show you the typical way that we use to find the insight, all right, to discover that. That is, use a transformation to change the structure. Yeah. If you do not change the structure, it's hard to find that relationship. So now a typical way that we use in real world problem solving, we do transformation. For a given expression, we need to change its form. The original form does not reveal the insight. After we change the form, we can get the insight easier. That's the idea. Yeah. Here, let me show you the transformation part. All right. What is the transformation here? For this particular problem, division operation. The question, why division operation? Yeah. So let us observe this expression first, the structure. Okay, the right-hand side, sum of several terms. Okay, each term, so here, try to find some property. Each term is a multiple of power of 2. Okay, multiple of power of 2. Yeah. Then it is quite natural we can consider division by 2. Quite natural because each one power of 2. Consider the operation integer division by 2. Okay, yeah. When you do that, except the first term, yeah, because the first term, when you do division by 2, it may not be an integer, yeah, division by 2. Okay, the first one, 0 or 1, be 0. Only 2 possible values, 0 or 1. Okay, yeah. Other than the first term, all the remaining terms, if you do division by 2, they are all integers. Okay, but the first term, if it's 0, still 0 after division. If it's 1, the fractional part will be drop it because we just consider integer division. Okay, we drop the fractional part. Yeah. So with this observation, now let us do division by 2, both sides. Yeah. So the left-hand side, we need to take the floor function because we only want to get an integer expression. Okay, yeah. And right-hand side, you can see B0 term is gone. Okay, no matter it's 0 or 1, after integer division by 2, that term is gone. Okay, all the remaining terms are still there. Yeah, but as for the power of 2, the exponent for each term, the exponent number is reduced by 1. Okay, yeah. So that is the structure change. Structure changes. So that is our transformation for this question. Okay, all right. Now you can see after we get this new expression, now we need to do some interpretation. Now, if this new expression can help us, get the answer easier. That's our goal. Find the answer easier. Okay, yeah, here. All right. Now let us go back to our recursive thinking last time. Here, we go back to the recursive thinking here. We need to use this recursive thinking here, all right? Yeah. Original problem here, original problem. Then after transformation, we get this problem different from original problem, but closely related. And we treat it as a subproblem. How about that? Subproblem. Because the problem size is smaller. Okay? The problem size is smaller than before, approximately 1/2 of the original size. Okay? So it's a subproblem. And you can see, in order to solve the original problem, we only need to solve a size reduced, a subproblem with size reduced. Okay, so here you can see we get the size reduction in this step. We just did size reduction. How about that? Size reduction. Okay, yeah. The smaller the size, the easier. And from the recursive thinking, when we can reduce the problem size, then we are very close to the recurrence relation to discover the recurrence relation. Here we are very close to that, right? Yeah, so it's actually in this recursive thinking, the critical step is discover some recurrence relation. That is the critical step. To discover an appropriate recurrence relation. Here, we want to discover that recurrence relation. Okay, all right. Before we can write it out, let us try to do some observation before we can write the recurrence relation clearly out. Okay, the observation. First, the least significant bit is removed. B0, the least significant. After division by 2, it is gone. Okay. It doesn't matter what the value it has, 0 or 1, it is gone. Okay. So that's the first observation. Okay. Second, the number of bits is reduced by 1. You just count the number of bits here. You have S bits, right? Little s bits. For the original question, you have S plus 1 bits. The difference is 1. Okay, so the number of bits is reduced by 1. The answer. Okay, yeah, the second observation. The third one, the problem size is reduced by half. Yeah, here, the problem size approximately, so we can treat it as half, okay, n over 2, floor function. Okay. With these 3 observations, now we can write the critical step, recurrence relation out easily. Okay, yeah, let us write it. Okay, let us use a special function to represent the number of bits for a given integer n. Okay, so that is here I call bin rec, recursive binary. Okay, bin rec of n. Yeah, this function gives us the number of bits representation, but in recursive way. Okay, recursive way. So we get a recurrence relation. So the left-hand side, bin rec of n equals the right-hand side, we find the answer of the subproblem with half of the size. Okay, bin rec of floor function n over 2, approximately half of the size, but you need to add 1 because the difference is 1. So you add that 1 back to that subproblem answer, to the answer of that subproblem. Okay, yeah. After that, then you have this critical step, recurrence relation. We know how to solve the problem with given recurrence relation, right? Yeah, but we need to have a base case. Base case, just bin rec this function when n equals 1, the number of bits also 1. Okay, yeah. So we discovered this recurrence relation, so we can solve it.